Hello everybody, in this question we need to prove that n to the power 5 minus n is divisible by 5 for all positive integers n. It's proof by induction, so that's what we're going to do. So then we will assume that at n equals 1, you would get n to the power 5 minus n. It's 1 minus 1 is 0, and which is divisible by 5. So I'll write that. Then we are going to do n equals 2, try out a few cases, n equals 2. So then n to the power 5 minus n would be 2 to the power 5 minus 2, and that is 32 minus 2. That is 30, which is divisible by 5. So then we make an assumption so that the statement holds true for n equals k. So if it holds true for n equals k, what we get is k to the power 5 minus k should be divisible by 5. So then, if it holds true for n equals k, we assume it would hold true for n equals k plus 1. So k plus 1. So then k plus 1 to the power 5 minus k plus 1 must also be divisible by 5. So we need to now show that k plus 1 to the power 5 minus k plus 1 is divisible divisible by 5. So how do we show that? So we are going to write k plus 1 to the power 5 minus k plus 1. So I can use another ink and it will probably be simple. So if I say k plus 1 to the power 5 minus k plus 1, so that is equal to, if I take k plus 1 outside the bracket, I would get k plus 1 to the power 4 minus 1. And then I can expand it using binomial expansion. That is equal to k plus 1. Then that would be k to the power 4 plus 4k cubed plus 4 times 3. That's 4c2, so that's 4 times 3 divided by 1 times 2 times k square plus 4 times 3 times 2 plus 1. Then I write the minus 1, that's this one. So then I can write this is equal to k plus 1 times, so k to the power 4 plus 4k cube plus 2, so 6k square plus 4k, because this would cancel out, plus 1 and minus 1. So we now multiply it out, so that we get k to the power 5 plus 4k to the power 4 plus 6k cube plus 4k square plus multiplying by 1, so k to the power 4 plus 4k cube plus 6k square plus 4k. So that is equal to k to the power 5 plus 4k to the power 4 and 1, so that's 5k to the power 4 plus 6k cube plus 4, so that's 10k cube plus 4k square, 6k square, so plus 10k square plus 4k. So you see these terms, they would be divisible by 5 because they are multiples of 5. So we are only left with the 4k and k to the power 5. So now if we go up and look, see we've already said here that k to the power 5 minus k is divisible by 5. So I could have written that here, so I missed writing that, so I should have written here that therefore k to the power 5 minus k can be written as 5 times p or any other, any constant. So where p is any positive integer, not a constant, sorry, any variable. So where p is any positive integer, so I can write where p is any positive integer. So when I write that, so I can just substitute, but I don't have it in this format yet, k to the power 5 minus k. So if I here, so I have k to the power 5 plus 4k. So I can now write this as k to the power 5 plus 5k minus k. So plus 5, leave this here. So then 5k to the power 4 plus 10. So that I can write as, I can take again 5 outside of the bracket. So then I can write this as 5 times k to the power 4 plus 2k cube plus 2k square. So then that is equal to, you see, k to the power 5 minus k, I can group it. I can write plus 5k, that's a multiple of 5, plus 5 times k to the power 4 plus 2k cube plus 2k square. So I can then, this is a multiple of 5, it's already a multiple of 5, so this bit is divisible by 5, and so is k to the power 5 minus k, because I have assumed it is equal to 5p, so k to the power 5 minus k is divisible by 5. So I can say that's equal to 5p plus 5k plus 5 times k to the power 4 plus 2k cube plus 2k square, and I can comfortably say which is divisible by 5. Hence, statement holds true for n equals k plus 1. Therefore, we go back to our original question. So therefore, n to the power 5 minus n is divisible by 5 for all positive integers n. So I'm going to write that n is divisible by 5 for all integers n, and hence my proof is complete.